Every so often, a single year comes along that just changes everything for a field of study. For mathematics, 2025 was one of those years. This was the year that problems that had stumped the greatest minds for over a century, they finally cracked. We're going to dive into how 3 of these absolutely monumental challenges were finally overcome. It sounds like the beginning of a bad joke, right? Colliding gas particles, impossible shapes, and a spinning needle. What could they possibly have in common? Well, the answer is that they are all at the very heart of mathematical quests that are over 100 years old. And in 2025, after generations of dead ends, all 3 were finally conquered. So here's what we're going to get into. We're going to tackle these 3 incredible problems. First, we'll see how mathematicians finally built a solid bridge between the microscopic world of particles and the everyday world we actually see. Then, we'll take a trip into these wild, unseen geometries that might just unlock secrets of the universe. And we'll wrap it all up with a surprisingly deep puzzle that starts with something as simple as a needle. And look, these aren't just any old problems. These are foundational questions, challenges laid down by the giants of the past, the kind of questions that have shaped entire branches of mathematics for decades. To solve even one is a huge deal. To solve all 3 in 1 year, that's historic. All right, so for our first story, we have to go way back. We're talking the year 1900. The legendary mathematician David Hilbert, he laid out a list of 23 problems that he thought would define the next century of math. His 6th problem was maybe the most ambitious of all, to build a rock-solid mathematical bridge between all the different laws of physics. And believe me, this was not a quick fix. The journey to get to a solution took 125 years. There was a huge step forward back in 1975, but that proof, it only worked for a tiny fraction of a second. It literally took another 50 years for a team to figure out how to stretch that proof out over any meaningful amount of time. Okay, so here's the core of the problem. You've got a gas, right? Well, physicists have 3 completely different ways of looking at it. On the tiniest microscopic level, it's just zillions of little particles bouncing around like billiard balls. If you zoom out a bit to the mesoscopic level, you start talking about the statistical behavior of those particles. Zoom out again to the macroscopic level we live in, and you just see the gas as a single continuous fluid. The challenge? Prove with pure, undeniable math that the tiny billiard balls in step 1 actually cause the statistical behavior you see in step 2. And the problem, the real wall they kept hitting, was just the mind-boggling scale of it all. You're not tracking 2 or 3 particles, you're tracking a number so large it's practically infinite. The number of ways they can all collide with each other becomes, well, as one of the mathematicians said, those collision histories are very, very, very complicated. That's putting it mildly. And there was one specific monster hiding in the math that everyone was afraid of: recollisions. This is what happens when 2 particles bounce off each other, go their separate ways, and then, sometime later, run into each other again. That second collision creates a kind of feedback loop that makes the number of possibilities just explode. For decades, nobody could figure out how to control that mathematical explosion. So how did they do it? Well, the breakthrough from Yu Ding, Zehar Hamani, and Sha Ma was just so clever. It came from a total shift in perspective. They realized they didn't have to track every single possible collision. Instead, they came up with this brilliant algorithm to prove that the really messy, complicated histories, the ones with all the nasty recollisions, are actually so incredibly rare that you can just ignore them. They proved the monster was too rare to matter. That was the key. Okay, let's switch gears. From the physics of tiny particles, we're now jumping into the mind-bending world of impossible shapes. This is the realm of hyperbolic surfaces, shapes that literally can't exist in our 3-dimensional world, but are absolutely fundamental to modern math. And it's a field that was truly pioneered by the incredible genius of the late Mario Marzicani. So what is a hyperbolic surface? Okay, picture a Pringle chip, or maybe a horse's saddle, that shape. Now imagine a surface that curves like that everywhere, at every single point. On a surface like this, parallel lines actually fly away from each other. Space itself seems to expand the further you go. It's a world that completely breaks our intuition, a world mathematicians can only explore with the language of equations. And you really can't talk about this field without talking about Maria Mirzakhani. She was a pioneer, the one who drew the first maps of this strange new world. People who knew her said she was just a superstar. Even though her life was tragically cut short, her work lit the way for a whole new generation to keep exploring. Now, the big question they were chasing is all about how connected these surfaces are. Think of it like this. Is the surface a well-designed city with tons of roads, making it super easy to get from any point to any other? Or is it a city full of dead ends and traffic jams? Mathematicians have a way to measure this, called the spectral gap. All you need to know is there's a magic number, 1/4. The closer a surface gets to that number, the better connected it is. The big mystery was, are most of these shapes more like the perfect city or the traffic nightmare? But, of course, there was a problem. A huge one. It turned out that a very small number of these surfaces had these weird, tangled-up pathways snaking through them. And these messy paths were like statistical outliers. They threw all the calculations off. It made it impossible for mathematicians Nalini Anantharaman and Lauren Lunk to prove what they suspected, that most of the surfaces were actually the well-behaved, well-connected kind. They were completely stuck. And this is where things get really cool. Anantharaman and Monk had this incredible aha moment. They looked at a completely different field of math, the study of random networks, like social media connections. And buried deep in a paper by a mathematician named Joel Friedman, they found a tool, a formula that they could adapt. And they used it to mathematically filter out all the badly behaved, tangled surfaces. It was like finding the exact right key for a lock nobody could pick. So you might be thinking, okay, weird shapes, so what? Well, here's why it matters. These abstract shapes, these impossible geometries, they can act as a kind of simplified toy model for some of the deepest and hardest questions in physics. By understanding the rules in these simpler imaginary worlds, we get brand new tools to help us understand incredibly complex things like quantum chaos in our own universe. All right, for our last story, we're going to look at a puzzle that sounds so simple you could explain it to a kid. But it turns out to be one of the deepest, most difficult problems in modern math. And it all started back in 1917 with a simple question about a needle. Seriously, think about this for a second. You have a needle, say 1 inch long. What's the smallest possible area you need to flip it around 360 degrees? Your gut tells you it's probably a circle, right? But the mathematical answer is absolutely shocking. You can do it in a region that has an area of 0. Yeah, 0. This crazy paradox led to a much, much deeper question that we now call the Kakeya conjecture. But here's the catch. That 0 area trick only works on a flat 2D surface. The moment you try to do this in 3D space, the problem it explodes in complexity. The challenge basically becomes this. Imagine you have a box filled with a bunch of tiny, thin straws, and each straw is pointing in a completely different direction. The conjecture says that you can't squish all those straws into a tiny corner of the box. They have to, by necessity, take up a good chunk of the box's total space. For decades, mathematicians tried to attack this with a method that was kind of like building a staircase, one tiny step at a time. But it had this fatal flaw. A flaw you can think of like the kids' game Telephone or Chinese Whispers. At every single step, a tiny bit of information was lost, it got a little fuzzy, and by the time you got to the end of the chain, the final message was total gibberish. The incredible breakthrough by Hong Wang and Joshua Zoll was discovering this hidden graininess in the problem, which let them control the information loss and make sure the message got through perfectly at every single step. It's just like the quote says, if you lose even a tiny bit of information at each step, the end result can be worthless. Wang and Zoll figured out how to basically plug all the leaks in the argument, making sure it was watertight from start to finish. So again, why does a puzzle about a needle matter so much? Because it was never really about the needle. It was about the foundation of a huge area of math called harmonic analysis, which is the math that describes everything from radio signals to quantum waves. This problem was the base of a whole tower of other ideas. And now that it's solved, that foundation is solid as a rock. Mathematicians can finally start building higher. So, let's just step back for a second. We've got a bridge connecting the tiny world of particles to our world. We have a new map for these incredible, unseen geometries, and we finally solved a century-old puzzle about space itself. I mean, when questions that have stood for over 100 years finally fall, it really feels like you're turning a page and starting a brand new chapter. And that just makes you wonder, right? Solving these massive problems, it's not an ending, it's a beginning. It opens the door to a whole new set of questions we haven't even thought of yet. And maybe that's the most exciting thing of all. What do you think the great unsolved problems of the year 2125 will be?